This is Tejaswini of registration number 18BEC0083 from slot A1 of serial number 13. I am here to present my digital assignment 2 of computer organization and architecture. The chosen research paper is low cost floating point arithmetic unit design. Coming to the first question, explain how the selected paper related to COA syllabus or curriculum. In this paper, we present the floating point arithmetic unit that improve the performance of multimedia processing with low hardware cost. Here we reduce the floating point arithmetic unit hardware area in two ways. First, by designing a percentage bit single precision architecture that can execute 64-bit double precision operation. And second, by implementing the simple architecture of an aligner, a sticky bit generator and rounding units. As we use the architectures of 32-bit which we learnt in my curriculum, some of the algorithms like multiplication and division were also present in my curriculum. So by these ways, this is related to the COA curriculum. Coming to the second question, draw the existing architecture discussed in the paper using appropriate raster graphics editor software. This is the existing architecture of floating point arithmetic unit. This is drawn using the draw.io tool. Here you can see this. See the block diagram which is drawn using draw.io tool. Coming to the third one, draw the tabulated results and graphs using Office suited in encapsulated PostScript file format. Here you can see the tabulated results. This is also shown in the draw.io tool. Here you can see and the graphs. These are the graphs which are output of the results. Coming to the fourth question, draw the proposed architecture discussed in the paper using diagramming vector graphics application software in encapsulated PostScript file format. Here you can see the architecture of single precision and double precision. Pipeline of design floating point arithmetic unit. You can see the pipeline of the FPAU which is drawn using draw.io tool. Coming to the fifth question, draw the transistor level internal diagrams using electronic schematic capture and simulation tools in the EPS file format. This is the transition level internal block diagram. Coming to the sixth question, compare the proposed architecture with existing architecture in your reference book. The proposed architecture, the data formats in floating point arithmetic unit that we designed handles the operations of IEEE 754 standard single precision and also the double precision formats. Each format has add, subtract, absolute, truncate, exchange and conversion instruction. The operation results are adapted to all IEEE 754 standard rounding modes. In single precision operations, two 32-bit operands are input into the floating point arithmetic unit and a 32-bit result is output for king returned to the register. However, in double precision operations, since the proposed FPAU has a 32-bit external data bus, to minimize the hardware cost, each of the two 64-bit operands and must be divided into two 32-bit exponent subtractor. This block generates the difference of two exponents for the alignment of smaller operand. Since the exponent of single precision format is an 8-bit and the exponent of double precision format is an 11-bit. The block needs 11-bit from two operands to support the single precision and double precision formats. In aligner, the aligner of proposed floating point arithmetic unit shifts the significance of smaller operand to the right by 0, 10, 53, bits to supply double precision operands. Comparison of swap logic. This block is used to compare two significants. The result of comparison is used for compare instruction and is also used to swap the significance of two operands. Significant adder. The significant adder has a 27-bit width for a double precision operations, which does not include IRSH because they are excluded in rounding control unit. Leading zero counter. The leading zero counter should be able to count up to 53-bit long data for double precision operations. Since this proposed architecture is a 32-bit structure, only 32-bit input is input into the functional unit. Sticky bit generator. A conventional mask sticky bit generation method generates a sticky hit from the shift value to select the hits of array. This method uses the shell value to determine which hits are needed to generate the sticky bit and then generates mask bits. Existing architecture inputs. RISC architecture characteristics. Simple instructions are used, and this also uses simple addressing modes and fixed length instructions for pipelining, and supports only simple data types and synthesize complex data types. RISC permits any register to use in any context. One cycle execution time. The amount of work that a computer can perform is reduced by separating load and store instructions. RISC contains large number of registers in order to prevent various number of interactions with memory. And RISC pipelining is easy as the execution of all instructions will be done in a uniform interval of time, that is one click. RISC uses Harvard memory model means it is a Harvard architecture. Multiplication instruction is divided into three instructions. Load, prod, store. Load moves data from memory bank to register. Prod finds the product of two operands located within the register. Stores moves from a register to a memory banks. Coming to the seventh question. List the advantages of proposed design over the existing design. Advantages. The first and major most advantage of floating point arithmetic units is its price. The design of architecture was completely based on the Harvard components that would not cost much in building the architecture. Apart from its cheaper price, it has also got another advantage, that it receives and responds 2 times faster than the existing design, which makes the design more valuable and satisfactory. The performance cost ratio is significantly improved. The proposed architecture has new operation units such as the aligner, a sticky bit generator, and rounding logics, which can reduce the hardware cost. This proposed FPAU has 3 cycle latency in single precision computations and 6 cycle latency in double precision computations. The total area of proposed floating point arithmetic unit is about 6590 equal gates. Next, 8th question. List the merits and demerits of proposed and existing techniques or hardware. Merits and demerits. The proposed and existing are compared here. Proposed, the instructions are less and need few registers. Reduced instructions need a less number of transistors. And coming to the proposed, there is no requirement of RAM. In existing hardware, large RAM is required to store assembly level instructions. Coming to the 9th question. This is the application of proposed design. The proposed architecture is used to carry the arithmetic operations. It can carry arithmetic operations with hardware components which cost less and comparatively in a low area of space. It reduces the floating point arithmetic unit hardware area in 2 ways. First, by designing a 64-bit single precision architecture that can execute 64-bit double precision operation. Second, by implanting this simple architecture of an aligner, a sticky operations. It has 3 cycle latency in single precision computations and 6 cycle latency in double precision computation. Draw the flowchart or algorithm or transition level circuit proposed in the design in encapsulated PostScript file format. For the single precision and double precision, these are drawn in the draw.io tool. Here you can see this is the single precision flowchart, and here comes the double precision flowchart. Thank you.